So we know that Ax equal to b is the fundamental equation of the linear algebra. So far we have assumed that A is a square matrix and b is in the column space of A, and hence Ax equal to b had a solution. And now if A is a column, if A is a matrix and a vector b, which is, if b is not in the column space of A as shown in figure here, then X has no solution. And now what is the idea? And now the idea is to use the concept of projection. It is projecting b on A and getting Ax equal to b. And here X is not this same X, but it is called as Ax cap, right? So now, yes, so now you can see here that when I'm projecting b, so I'm getting a new point here, that is the p, and this represents the vector p. Okay, and now another way to see the matrix is through its physical appearance. And now if A is a rectangular matrix, Ax equal to b is often unsolvable, which implies that rectangular matrix, okay, that there are in the rectangular matrix there are either more unknowns than the number of equations, or less unknowns than the number of equations. In such a scenario, we would depend upon A transpose. So the matrix A transpose A will help us to find the vector X cap, right? That comes, so the solution through this A transpose will come as close as possible to solving Ax equal to b. And now let us see physically, let us see that suppose A is a matrix, rectangular matrix. I multiply A with A transpose and then it becomes a square matrix. And the equation Ax equal to b gets modified as A transpose A X cap equal to A transpose p. So now when we try to simplify A transpose A, we get a square matrix. A transpose B, we get another vector here, we get it, and then we need to solve X cap. So X cap is the approximate solution to this problem. And now the concept of projection is a foundation for many problems. Okay, and it gives, so the projection concept also gives the idea of solving the problem through least square, and the statisticians call this problem as regression line fitting, which projects the points parallel to the y-axis, or it is perpendicular to the x-axis. So another famous application based on this particular concept is the principal component analysis, which involves the orthogonally projecting the points, okay, orthogonally projecting the points onto the projection axis. So now we should, so there is a distinction between the regression line fitting and principal component analysis projections, so which we will see in the upcoming lectures. So now orthogonal vectors and subspaces. What is a basis? A basis is a set of independent vectors that span a particular space, and geometrically it is a set of coordinate axes that are perpendicular to each other, right? In my previous lecture I had already shown that the standard basis vectors, right? So just I'll take the pen. So now you can see that the standard basis vectors can be represented in 3D. I can say that this is x is 1 and y is 0 and z is 0. So this is the coordinate of the x-axis, and coordinate of y-axis 0, 1 and 0 is a coordinate of this y-axis, and z-axis you can say that it is 0, 0, 1, right? So this forms the standard basis for for means in three dimension. And now in choosing the basis, we tend to choose the orthogonal basis. So now this is the standard basis. Now we can see that all three vectors are orthogonal to each other. Now the interesting thing is that this is the standard basis vectors, right? These three. Now if you rotate this these vectors, now you will get, like, for example, if I take another color here, and then I can show you that, see, this is, if I rotate this plane, then I will get another set of basis vectors, and those are not standard basis vectors. That we should keep it in mind, right? So now subspaces can be perpendicular. So another concept is that subspaces can be perpendicular to each other, and the fundamental subspaces meet at right angles. So I'll show you this diagram. You can see here, given a matrix A, will have column space, okay, will have row space, and the row space will be, that row space is represented as C of A transpose. So row space is perpendicular to the null space of A. On the other hand, column space of A is perpendicular to null space of A transpose. Okay, so these things already I have explained in the linear transformation lecture. Hope you remember that. Now 4 subspaces are perpendicular in pairs. 2 in Rm, so these 2 are in Rm, and 2 in Rn. And now row space is perpendicular to null space of A, which I have already told. And now column space is perpendicular to null space of A transpose. And one subspace is orthogonal to other subspace, which means so now if I say that this subspace is orthogonal to this subspace, which implies that every vector in one space is orthogonal to every other vector in the other subspace. So if I choose any vector from here, so it is natural that these two vectors will be orthogonal. So that is the idea in this slide. And now row space is row space is orthogonal to null space of A. What is the meaning? Row space is orthogonal to null space of A, which implies that if X is a vector, right? If X is a vector in a null space, then when we multiply a matrix, that is AX, when we do AX, the output is 0 because X is in the null space of A. And now pictorially representing the same Ax equal to 0 here, we can see that this is a matrix A, okay, and this is the column X. Now you see that because I have told that the vectors in the null space are orthogonal to the row space. So you take this row 1 and multiply with this column elements, and then you will see that you will get it as a 0. That means row 1 is perpendicular to this X vector. Similarly, row 2 is perpendicular to this vector. Similarly, you can see that all the rows, okay, when they multiply with this vector in the null space, they give 0. This means that the dot product of every row in A, okay, and X is 0. What does it mean? That means they meet the rows and the column X, they meet at right angle. Okay, so the angle between them is 90 degree. Hence, they are called as orthogonal. So now let us see one example. This is some plane which I have drawn, and I have taken V2 and V3 as two vectors. So what I do is that at the corner I have one more vector, that is V1. Now in this case, if you take any vector, in this plane, which is in yellow color, it is shown here, and if you take any vector here, those vectors will be perpendicular to this vector V1. So that is what I have shown here. So all the vectors are in this space are orthogonal to V1. On the other hand, if I take two vectors V1 and V2 in this particular plane, then I have another plane represented in blue color, which is V3. We can see that V1, Okay, v1 may be perpendicular to v3, but v2 is not perpendicular to v3. So that is the idea. What does it imply? This implies that not every vector in the subspace is orthogonal to other subspace vector, and here v2 and v3 are not orthogonal. So that is the key thing which we should remember here. And orthogonal is the another word for perpendicular or forming a right angled triangle, which we should remember. And length of a vector is also called as the norm, okay, which in the literature of machine learning, image processing, you can see that this norm is being very popularly used here. It is represented by the modulus x symbol, which we have to remember. So what is modulus x? In two dimension, it comes from the hypotenuse of the triangle. Now, if you have two vectors, okay, and they meet at right angles, then the length will be then the length will be the hypotenuse, right? That is what it is being conveyed here. So I've shown one example. You can see this is the x plane, this is the x-axis, this is the y-axis. I have vector 2 and 3, and this is the coordinate representation, and now this is the x value, this 3 is the y value, and now if I what is the length of this vector 2, 3? So the length of this vector is root 13, because the formula is length in 2D, which is x square, is equal to x1 square plus x2 square, which is square root of x1 square plus x2 square, which implies 2 square plus 3 square, which is 4. 4 plus 9 is, okay, root 13. So that is what is the in case of 2 dimension. Let us see in 3 dimension. So there are 3 vectors in this 3 dimension, and yeah, so these are the coordinate axis. And now suppose if I take a vector x here, okay, now this vector x represents all 3 components, that it has x, y, and z component. So that is the value you can see 1, 2, and 3. And what is its length? This length is root of 14. How did we get that? So we got through this extension of this formula, like square root of x1 square plus x2 square plus x3 square will give this length root 14. Similarly, we can see that another vector I have drawn here with dotted lines. You can see here the vector involves only, if you can tell that this is x, this is y, so it involves only x and y component, whereas z component is 0 in this particular case. And now, what is the length of this? The length of this vector is root of 5. So the formula is shown here. We can see here x1 square plus x2 square plus x3 square is the formula here. And now how to how do we show the orthogonality of the vectors? So length of the vector is also represented. Okay, it is represented by as x transpose x. So we can see here what is x. X is a vector which is lying down, right? X is a vector which is lying down. So I am representing another vector, same vector. If I want to represent as a column, then I would use x transpose as a symbol. You can see here same vector 1, 2, 3. It was sleeping vector here, and now you can see that if I use x transpose, it becomes standing vector. So this representation is popularly used in case of matrices, right? So usually this is the matrix representation here. So now when we multiply this, it becomes same 1 into 1, 2 into 2, minus 3 into minus 3. The value becomes 12 plus 22 plus 32 plus 32 is equals to. I think there is a mistake in this. It is it is 1 plus 4 plus 9 it is. Okay, so there is a mistake here in this slide. So I'm multiplying this corresponding values and then adding it. So here it is, this is actually root 14, yes. And now two vectors are orthogonal if their inner product is 0. So this is a very fundamental idea. So if two vectors are orthogonal, then their inner product will be 0. So how they will be represented? They will be represented by two vectors, x transpose y. So y is a sleeping vector and x transpose is a column vector, right? When we multiply this, then we get it is as an answer. Sorry, here there is a mistake, xn and yn here. So it gives us 0. So the physically how so geometrically how you see that? Suppose there are two vectors. These are the two vectors. So vector x and vector y. So when you multiply this, you will get the inner product, that is the dot product of these two vectors is 0. That implies that these two vectors are they meet at 90 degree. Okay. So what happens when the value, right, x transpose y is greater than 0? So x transpose y, if the value is greater than 0, then their angle is less than 90 degree, right? So this is the clue for us that so here I have shown one example. You can see okay, this is a vector, this is another vector, right? Sorry, this is the vector, this is another vector. So the angle between them, the value between them is greater than 0. That implies that their angle is less than, okay, it is greater than 0. So the angle is less than 90 degree. On the other hand, if x transpose y is less than 0, that implies that their angle is greater than 90 degree. So I have shown geometrically here. You can see if these two are the vectors and then x transpose y is less than 0, that means that this is more than this means that their angle is greater than 90 degree. And x transpose y generally refers to matrix X. So usually we multiply matrix times a vector, right? So this is represented as x transpose and this is a vector y. So every row will be every column. Suppose if we represent in this manner, then every row will be multiplied by by this particular column. So if non-zero vectors v1, v2, vk are mutually orthogonal, then those vectors are linearly independent. That is the idea. So orthogonal, show that the two vectors x and y are orthogonal. Now I already told in the previous slide that if x and y are orthogonal, then they will be meeting at 90 degree and the dot product is 0. So let us check now what is the dot product of x and y. 1 into 2 is 2, 2 into minus 1 is minus 2, 3 into 0. So plus 2 minus 2. So the answer is 0, 0. The dot product is 0. Hence x and y are orthogonal. So which we can see here, the dot product is 0. And how to prove that x transpose y equal to 0? So this is through the Pythagoras theorem. So Pythagoras theorem, we take two vectors, they meet at right angle. So now this is x value, this is y value, this is x plus y value. So now you try to expand this. Right? Already I have drawn this. So let me erase this. Yes. So already I have shown some diagram here. So I will remove that. So now you can see that this is x, this is y, so this is x plus y, and now you will expand this. So x square is represented as x transpose x, and y is represented as y transpose y. Similarly, x plus y is x plus y transpose into x plus y. And now when you try to simplify this one, right, then x transpose y, x transpose x, and y transpose y will get cancelled. Okay, and you will be left out with only x transpose y, and this implies that x transpose y equal to 0. So this is a proof to show that the two vectors are orthogonal. And now vectors with x transpose y are orthogonal. So this we know that, right? If there are two vectors, if their x transpose y, if their dot product is 0, then they are orthogonal. So now it comes the very interesting question: what happens when their inner products that are not 0, right? And angles are not right angles. So this is a very fundamental idea, right? If they are if the dot product between the two vectors are not orthogonal, okay, then what is the use of that? Okay, what does it represent? Suppose we want to find the distance from a point B, right? A distance from a point B to the line in the direction of the vector A, right? So this is the concept of least square, right? Least square fitting. So that is the idea. You have been given set of points, and that point should be projected onto the line which you are trying to fit it. So projection P is the point closest to B. So I have shown here. You can see, suppose B is a vector, and now B is the vector which you want to project onto the axis, that is A, and it makes an angle theta, and we can see that B is orthogonally, it is projected onto the A, and it makes a 90-degree. And now that vector is represented as A, this in the red color you can see here. And now P, that is represented as a P. So P is the projection of B onto the line through A. So P, the point P is called the projection, right? This point is called the projection of B onto the line through A. So this is a very fundamental idea. We will be using this to solve many problems in this coming lecture, right? And another important thing which to observe is that, see, because I try to approximate B through P, right? So now there is an error. What is the error? Error is E equal to actual B minus P. What is P? P is the projected value. So this is the true value, and this is the projected value. So true value minus projected value will give you the error E. And this is what we try to use in case of minimization problem, right? We try to minimize the error while fitting the regression line. So this problem leads to least square solution to an undetermined system. Vector B represents the data. So all these vectors represent the data from the experiments. In economics, statistics, it is called as the idea is called the regression analysis. So now see a very related concept. It is the cosine of the angle is directly related to the inner products. So now suppose I have a unit vector which is represented as 1, 0. If I rotate it with an angle theta, then my points become cos theta and sin theta, right? And now let us try to get the cosine of the angle between the two vectors. So suppose A is a vector which is with the coordinates A1 and A2, right? And now what I do is that I try to project this A onto the x-axis, okay, x-axis, and that is represented as Q. So now OAQ represents a OAQ represents a right angle triangle, and the angle is represented as an right angle triangle, but the vector A is making an angle alpha with the x-axis. So that is the key here. Similarly, I will have another vector, and the length of this vector is represented as the modulus of A, norm of A. So what it is square root of A1 square plus A2 square. Similarly, I will have another vector. So the another vector whose the coordinates are B1 and B2, and now the norm of this B is modulus B, and now it is making an angle beta with the x-axis. And now you can see that what is the this vector is making an angle beta, this vector is making an angle alpha with x-axis. Now my interest is to find this theta. What is the angle between the two vectors A and B is the theta. So how can I represent? Theta is beta. Theta is equals to beta minus theta is equals to beta minus alpha will give you the theta. So now let us try to get the cosine formula, right? Cosine of the angle theta. So now we can see that by the law of parallelogram, we can see that this vector, right? This vector is represented as B minus A, right? And the length of A is the hypotenuse in the OAQ triangle. And sine and cosine of alpha and beta, we can derive it. Now, what is sine alpha? Sine alpha is, so what sine alpha is a2 divided by norm of a. Similarly, sine beta is b2 divided by norm of length of b. Similarly, yeah, it should it should have been a2, right? Similarly, cos alpha and cos beta, we can see here, this is the formula. Now, what is the cosine of theta? Cosine of theta is beta minus alpha, which I have already told you. So now apply cos theta on both sides. We get cos theta is equals to cos beta minus alpha cos beta, which is equal to cos beta into cos alpha plus sine beta into sine alpha, which implies a1 b1 plus a2 b2 divided by a and length of a and length of b. So this is similar to cos theta is now dot product of the two vectors, which is shown by a1 b1 plus a2 b2. So now here we can see that, okay, we can see that a transpose b, right? A transpose b is the dot product of the two vectors and the length of the two vectors is shown. So this is the formula for cos theta.